Now this section is called inverse functions, and so far all we've talked about are one-to-one functions. The reason for that is because in order to have an inverse function, it has to be one-to-one. So to have an inverse function, it has to be one-to-one first, because the concept of an inverse functions mean that you swap the x and y values. That's how you get an inverse function. And in order to swap the x's and y's, neither one of them can repeat. And that's the goal here. So with our inverse functions, we are swapping out those x and y values. So that's how I know. So if we have an inverse graph of an inverse function, it could look something like this. So if I'm looking at my graphs of my inverse functions, this is what we actually have. So you have your chart here. This blue dashed line, this is the line of y equals x. So if I'm looking at my line here of y equals x, the purpose of your line of y equals x, let's label it here. That's just your identity. So that line that goes up through there, that's just your identity line. So y equals x, it has a slope of 1, a y-intercept of 0. That's just your y equals x line. Now this red graph is just a graph here with this red one. So it's going to go up like this. It's one-to-one, just red by itself, because the x's don't repeat and the y's don't repeat. So we're good there. And then purple here is also a one-to-one graph. The x's don't repeat and the y's don't repeat. So if we look at those independently. Now, if I'm looking at these points, let's say I have this point on this graph right here. So then this is going to be, let's say, 1, and then this goes over 2. So this is the point here of 2, 1. You are going to have that exact same point on your other graph. So if this is 2, 1, then I'm going to have the point right here that is 1, 2. And that's what I mean by the x's and the y's swap. Notice where they are. They are reflecting over this axis. This y equals x line here. It's a reflection back and forth where the x value input is a 2 and the output is a 1. On the inverse function, they're just swapped. You have a 1 for the input and a 2 for the output. That's it. That's the whole purpose of an inverse function, and why the x's and the y's cannot repeat to be one-to-one first. Then you swap those out, and then that's what your graphs look like. Cool. Let's look at this analytically. Whenever I go through and I'm trying to determine if functions are one-to-one, you can do a composition of functions. So remember back previous information into the current lesson. Remember back whenever we said a composition f of g of x and g of f of x. If you compose these two functions, it doesn't matter which one you do. They're the same. So either one, you plug the g of x function into the f of x or the f of x into the g of x, and all you get out of the deal is an x, then you know that these are inverse functions. So that is our criteria and what we're going to look at next. On this one, I want to determine if these functions are inverses, so we are going to do that criteria. If I have f of g of x or g of f of x, and they both give me x, then we're good to go. It's up to you. We only have to do one. I'm going to do both just so that you can see it. So let's look at this one here as number 1, try. I'm going to do f of g of x just so that we can have that. That means I have my g of x function here that I'm going to plug into my f function. So I'm going to take this g of x function and I'm going to plug it into the f function and see what we come up with. So I have all of this g of x is going in place of my x. So the cube root of x plus 1, this whole piece is going in there. And so then that is cubed minus 1. And that's what we're talking about there. So the cube here and the cube root cancel. And I'm now left with x plus 1 minus 1. The plus 1 and the minus 1. And I just have x. So if I have f of g of x equals x, that is the criteria is met. So yes, these are inverses. Yay! Remember, you do not have to do both of these. I am doing both of them just so that you can see what's going on here. So let's try this next one. I am now going to take my f of x function and plug it in place of my g of x function. So I now have the cube root of x cubed minus 1 plus 1. So I have plugged in this x cubed minus 1 in place of the x value. So I've just replaced this x with the x cubed minus 1. Now we simplify. The plus 1 and the minus 1 go. I now have the cube root of x cubed, and the cube root both go. So g of f of x equals x. Yep. These are still inverses, and we already knew that from our first test that we did. And that's the thing. It does not matter which one you do. You only have to do one. Okay, let's try another example. All right, I put a rational one in here because that always wigs people out. So with this rational one, we only have to plug it in once. Now here is my suggestion. Take a look at these. Which one's the easiest? This f of x only has one x involved. This one has two x's, so you'd have to plug it in twice. Don't do that. Take this g of x function, plug it in one time, and go with it. So if I have f of g of x here, I now have a 2 over 6x plus 2 over x, that's all in place of the x, plus a 6. Now, this is a complex fraction. Anytime you have a complex fraction, you want to multiply through by the common denominator. So each one of these terms has a denominator. The 2 and the 6 both just have a denominator of 1, so we're really not worried about that. My common denominator here is going to be this x. So I'm going to multiply both the top and the bottom by an x, just so that we can eliminate that. So 2 times x is a 2x. This x gets canceled out, and I just have a 6x plus 2. There's no x down over here with this 6, so I now just have a plus 6. So I have 2x over a 6x plus 8. Is there any possible way that I'm going to be able to break this down to simply an x? No! These don't cancel. There's nothing canceling out here. So if you end up with anything other than just an x, you're out. There's nothing else you can do about that. These are not inverses. So I wanted to show you an example of what it looked like to not have an inverse and something that was rational, because those complex fractions usually throw you for a loop. The deal with a complex fraction, you just have to find that common denominator. Once you find that common denominator, then you multiply the top and the bottom by that same common denominator to eliminate it. Cool. Let's do some more. All right. For these problems, instead of just having equations that we're looking at, we're going to find the inverse of each function that is 1-to-1. So in order to find an inverse, remember we said it has to be 1-to-1 first. So as soon as I determine that this is 1-to-1, then I can find the inverse. Okay, so let's think back. What was the criteria in order for this to be 1-to-1? It's a function, so the x's can't repeat. Good. And specifically, what else cannot repeat because it is 1-to-1? The y's. Good. So neither the x's or the y's can repeat. So let's take a look. In this f function, is there anything that is repeating in this one? Ha-ha! So here, my x's are all cool, but check this out. I've got a 1 and I've got a 1. I've got a 2 and I've got a 2. So if one thing repeats, you're out. But especially in this instance, I have a couple things repeating. So is there any way for me to find an inverse? No. Nope. Because this is not 1-to-1, there is no inverse. So the very first thing you want to look for is if this is 1-to-1. If not, shoot, you're done. If it is 1-to-1, then you find an inverse. Cool. Let's look at this part B and see what we can pull off. Is this one legit? Is it 1-to-1? Yeah. 3, 0, 2, 4. That's all cool. 1, 2, 3, 0. That's all cool too. Now, I have a 3x and a 3y, but no one cares. It's the same thing with the 0. As long as it's not in the same category, you're good. It's not just a number in there in general. I want to specifically only look at the x's and compare those. Then stop, go back, look at the y's, and compare the y's just by themselves. And so this one is cool. So this function is 1-to-1. Now let's find the inverse. The symbol for inverse looks like to a -1 power. So whenever I write this as an inverse, I'm going to write g looks like to the -1 power, but that is the symbol for inverse. So anytime you're trying to write the inverse of a function, that function to that -1 power is what means inverse. All right? Okay, cool. So g inverse here, so the inverse function of g, remember the concept of a inverse is that your x's and y's swap. So literally, that's all we're going to do. Swap those x's and y's. My first point is now going to be a 1, 3. My second point is a 2, 0. My third point is a 3, 2. And my last point is a 0, 4. That's it. Pretty sweet, right? Determine it's 1-to-1. Swap around those x's and y's and you're done. Cool. Now let's figure out what it is we just talked about. So if we sum all of this up, let's just talk about what this is. So in order to have a 1-to-1 function, the x's and the y's, neither one can repeat. So the x's and y's, neither one can repeat. In order to determine this, if I'm given a graph, you can use the horizontal line test. So that's how you can look at this if you're given a graph. Or if I'm given functions, I know that x can't be to an even power. So if x is to an even power, zoop, we're out. If it does not pass the horizontal line test, boop, you're out. So, and we're looking here, the x's and y's also cannot repeat. So those are our 3 criteria to get it 1-to-1. Once I get a 1-to-1 function, then we can look at our inverse functions. And we swap out those x's and y's. If I'm just having a function, I can swap out those x's and y's. Or if I have 2 functions and I want to determine if they are inverses, just do a composition. You can either plug the g of x function into the f of x or the f of x function into the g of x function. And as long as you simply get an x out of the deal, then you're good to go. All right, go get busy on that homework and rock the socks off this thing.